Every bridge in America stands on something you can't see. Wooden piles. Tree trunks pounded 40 feet straight down into riverbeds, into mud, into solid rock. In the 1800s, before concrete foundations, this was how you built a bridge. You took a tree trunk, sharpened the end, stood it upright, and hit it. Again and again. The machine that did the hitting weighed 2 tons and dropped from 40 feet. The sound could be heard for miles. This is the story of the steam pile driver, the machine that built the skeleton of American infrastructure, the machine that made railroad expansion possible, the machine that killed more men than most people realize. And the men who operated it? They stood inches away from a 2,000-pound hammer falling at terminal velocity, 60 times an hour, 10 hours a day. One wrong step, one frayed cable, one moment of inattention, and you weren't just injured, you were gone. But before we get to the machine itself, you need to understand what problem it solved. You need to understand what's underneath a bridge. Because most people have never thought about it. They drive over bridges every day without once considering the question that haunted every engineer of the 19th century. How do you build something heavy on top of something soft? Think about it. A river has a bottom. That bottom is mud, silt, sand, gravel. Sometimes clay, rarely solid rock. You want to put a bridge across that river. The bridge needs to hold locomotives weighing hundreds of tons. The bridge needs to hold that weight for decades, centuries ideally. You can't just set stones on mud. The stones sink. You can't build a pier on sand. The sand shifts. The water moves it. Your pier tilts. Your bridge collapses. People die. So what do? The answer is older than Rome. You drive piles. A pile is nothing complicated. It's a log, a tree trunk, stripped of branches, sometimes with the bark left on. The bottom is sharpened to a rough point. Not sharp like a pencil, sharp like a chisel. A blunt wedge that can split through soil and displace gravel without shattering. You stand that log upright. You hit the top. The log goes down into the earth. You hit it again. It goes down further. You keep hitting until the log won't go down anymore, until it hits something solid, or until the friction of the soil gripping the sides of the log equals the force of your blows. Then you do it again, right next to the first one, and again, until you have a cluster of logs standing vertically in the riverbed, their tops sticking out of the water, their bottoms anchored in something stable 40 feet below. That cluster is your foundation. You cap it with timber. You build your pier on top. The pier holds the bridge. The bridge holds the train. And the whole thing works because those logs aren't going anywhere. The Romans knew this. Julius Caesar's engineers drove piles into the Rhine in 10 days to build a bridge that still astonishes military historians. They used a device called a pile driver. Men hauling ropes. A heavy weight lifted and dropped. Crude, but effective. The Venetians knew this. Venice itself is built on wooden piles. Millions of them. Driven into the lagoon floor by hand in the 5th century. Alder wood mostly. Still holding up buildings 1,500 years later. The entire city, the palaces, the churches, the foundations of Western art and commerce, all of it resting on logs pounded into mud before the fall of Rome. But here's what the Romans didn't have. Here's what the Venetians didn't have. A railroad. A railroad is a hungry thing. It doesn't care about rivers. It doesn't care about valleys. It doesn't care about swamps. The railroad goes where the railroad goes, and everything in its path either gets moved or gets crossed. Between 1830 and 1900, America built over 100,000 miles of railroad. And those 100,000 miles crossed rivers. Thousands of rivers. Tens of thousands of creeks, streams, and waterways of every description. Every major river system in the country needed multiple crossings. The Mississippi alone required dozens of bridges along its length. Each bridge needed foundations. Each foundation needed piles. And here's the math that changed everything. A single bridge pier might require 40 piles. A major bridge might have 20 piers. That's 800 piles for one bridge. Driving a pile by hand, with a crew of 8 or 10 men hauling on ropes, dropping a weight, hauling it up, dropping it again, took hours. Days sometimes, depending on the soil. Hitting bedrock could take a week of continuous effort for a single pile. At that rate, a single bridge could take years to complete. The railroad didn't have years. The railroad had investors, competitors, bond payments coming due. A country expanding westward so fast that fortunes were made and lost based on who got there first. The solution wasn't more men. The solution was steam. If you're finding this useful, hit subscribe. I cover the forgotten machines and dangerous jobs that built America every week. Now let me show you what a steam pile driver actually was, because the machine itself was a marvel of brutal simplicity. Picture a tower, 40 feet tall, sometimes 50, made of heavy timber in the early years, later iron and steel. Massive beams bolted together, braced against any conceivable force. At the base, a steam engine. The same basic engine that powered locomotives, factory equipment, riverboats. Burning coal or wood, boiling water, converting heat into mechanical power through the expansion and contraction of pistons. At the top of the tower, 2 iron rails running vertically, like train tracks but pointed at the sky. And riding those rails, a weight, the hammer. Sometimes called the ram, sometimes called the monkey, sometimes simply called the weight. This hammer weighed anywhere from 1,200 to 3,000 pounds. Later models pushed to 5,000 pounds. Some specialized machines went heavier still. It was solid iron, a block of metal the size of a whiskey barrel, polished smooth where it rode the rails, its bottom face flat and true. Here's how it worked. The steam engine turned a drum. The drum wound a chain, heavy iron chain, links thick as a man's wrist, tested and inspected and replaced regularly. The chain lifted the hammer, smoothly at first, then accelerating as it rose. When the hammer reached the top of the guides, a trigger released it, a cam mechanism, later a clutch system. The chain went slack. The hammer dropped. 40 feet of free fall, accelerating the whole way, gravity pulling at 32 feet per second squared. At the bottom, it struck the pile. A log standing upright in a guide frame, waiting to be driven into the earth. The impact transferred all that energy straight down. The pile moved. 1 inch, 2 inches, sometimes 6 inches on a good strike in soft soil. Then the steam engine turned the drum again. The chain caught the hammer, lifted it. The trigger released. The hammer dropped. Another strike. 60 times a minute. Some machines could manage 80. The better operators found a rhythm. Blow after blow after blow. Hour after hour. Day after day. The physics of this deserve attention. A 2,000-pound hammer falling 40 feet reaches a velocity of approximately 50 feet per second at impact. That's about 34 miles per hour. The kinetic energy at impact is roughly 38,000 foot-pounds. Every single blow. For comparison, a modern car hitting a wall at 35 miles per hour generates roughly similar energy. Now imagine that impact. 60 times a minute, concentrated on a point about 12 inches in diameter. For hours. For days. For the entire construction season. The sound was extraordinary. Not a single crack. Not a boom and then silence. A rhythm. A deep, percussive thunder that you felt in your chest before you heard it in your ears. Witnesses described it as artillery fire, as thunder that wouldn't stop, as the heartbeat of industrial America pounding in their bones. From a mile away, you could hear a steam pile driver at work. From a quarter mile, the sound was physical. It moved through you. It shook loose fillings. It startled horses and sent dogs howling. It made conversation impossible. Workers who spent years near these machines went partially deaf, not from a single loud noise, but from thousands of impacts, tens of thousands, hundreds of thousands over a career, accumulating damage until the world grew muffled and distant. And the vibration. When that hammer struck, the energy had to go somewhere. Into the pile, yes. Into the ground below the pile. Into the frame of the machine. Into the barge if you were driving in water. Into the bones of every man standing nearby. The ground shook. Dishes rattled in houses a quarter mile away. Nearby buildings developed cracks. Windows rattled in their frames. Plaster fell from ceilings. If you drove piles too close to an existing structure, you could damage it, shake it apart, brick by brick. Insurance claims from pile driving damage filled courthouse dockets for decades. There are records of entire streets being damaged by pile driving operations. Foundations cracking, walls separating, chimneys collapsing. The men driving the piles kept driving. The claims would be sorted out later. The bridge had to be built. But here's what that violence accomplished. In 1 hour, a steam pile driver could do the work that took a hand crew all day. In 1 week, you could drive every pile for a bridge pier. In 1 month, you could complete foundations that would have taken a year by traditional methods. The railroad moved at the speed of steam, and the steam pile driver moved at the speed of the railroad. Let me show you how it actually operated in the field, because the machine itself was only part of the system. The logistics around it were just as complex. First, you needed piles, thousands of them for a major project. These weren't milled lumber, they were whole trees. White oak was preferred in the east, dense, strong, rot-resistant when submerged. Douglas fir in the west, straight-grained and available in extraordinary lengths. Cypress in the south, for its legendary resistance to water damage. The trees needed to be straight, at least a foot in diameter at the butt end, often more, and long, 30 feet minimum, 50 feet for deep water work, 60 feet or more for the worst crossings, where bedrock lay far below the surface. Selection was critical. A crooked pile was useless. Even a slight curve meant the pile would wander as it was driven, missing its target, fouling the foundation pattern. A pile with internal rot would shatter under the hammer, sending splinters flying like shrapnel, wasting hours of work. A pile that was too green, too freshly cut, would check and crack as it dried. Too dry, and it became brittle, prone to splitting. The sweet spot was timber cut 6 months to a year prior, properly stored away from direct sun and rain, straight-grained, and free of major defects. Getting these trees to the worksite was its own logistical challenge. You felled them in the forest, often miles from any road, stripped them of branches, skidded them to water or wagon roads, transported them by river, by rail, by ox team. A single bridge project might require 1,000 logs, each weighing several tons. Moving them was as much work as driving them. Entire logging camps existed solely to supply pile timber for railroad construction. Once on site, the logs were prepared. The bottom was shaped to a point, not carved fine, roughly hewn with axes and adzes. A 4-sided taper, or a more complex shape depending on the soil expected. Sometimes metal shoes were fitted, iron caps that protected the point and helped it penetrate harder soils. These shoes were expensive, but for certain conditions, essential. Gravel beds, compacted clay, rocky ground that would splinter an unprotected point. The top was cut flat and fitted with an iron ring, a band that kept the wood from splitting under repeated blows. Without that ring, the hammer would mushroom the top of the pile, spreading the fibers outward, eventually destroying the pile before it was fully driven. The ring was pounded on tight, a few inches down from the top, creating a reinforced surface that could withstand thousands of impacts. Then the pile was positioned. This was the dangerous moment. The pile had to be hoisted upright, lifted from horizontal to vertical using cranes, block and tackle, shear legs, or raw muscle power. A 40-foot log weighing several tons, swinging through the air, controlled by ropes and the skill of the crew, guided into the leads of the pile driver. Leads were the vertical guides that kept the pile straight as it descended. If a pile went in crooked, it was useless. Worse than useless. A crooked pile could lean against its neighbors, destabilize the entire cluster, force the engineers to start over. Positioning a 40-foot log upright on a rocking barge in a river current required extraordinary skill and coordination. Teams of men working ropes, a crane operator managing the lift, a foreman calling signals over the noise of the steam engine and the chaos of the work site. One miscommunication, one slip, one gust of wind at the wrong moment, and that log could swing, kill someone, crush a leg, destroy equipment, set the project back days. With the pile in position, the hammer began its work. The first blows were the hardest. The pile had to break through the surface layer, punch through roots if there were any, displace the initial soil. Early strikes might move the pile a foot on good soil. As it went deeper, resistance increased, the soil gripping the sides, the point encountering denser material. Strikes that moved 6 inches became strikes that moved 2 inches, then 1 inch, then half an inch. The foreman watched carefully. He counted blows, measured penetration with a marked pole. When 10 consecutive blows moved the pile less than a specified distance, usually a quarter inch or less, the pile was considered driven. Refused, in the technical language. It had reached a point where additional driving would do more harm than good. Split the pile, damage the point, waste time and fuel. Then the hammer was lifted clear. The pile stood alone, its top projecting from the water or the mud, and the next pile was positioned, and the process began again. A skilled crew could drive 30 piles in a day. Some records show 40, each one taking between 30 minutes and 2 hours, depending on conditions. Day after day, pile after pile, week after week, until the foundation was complete. But I haven't told you about the men yet, and that's where this story gets dark. Operating a steam pile driver was one of the most dangerous jobs in 19th century construction. And that's saying something, because 19th century construction was a slaughterhouse. Start with the obvious hazard, a 2,000-pound hammer falling 40 feet. The kinetic energy in that impact could crush a man to paste. A direct hit wouldn't leave enough to bury, and men got under that hammer. They had to. Someone had to position the pile. Someone had to fit the iron cap. Someone had to clear debris when a pile shattered. The rules said to only approach when the hammer was locked at the top. The reality was messier. Production pressures, foremen demanding speed, men taking shortcuts because that's how you finished early and got paid and went home. And sometimes the lock failed. Sometimes the trigger released accidentally. Sometimes a man misjudged the rhythm and was where he shouldn't be when gravity did its work. The records are fragmentary. Companies didn't keep detailed safety statistics, but newspapers of the time mention these deaths casually. Worker killed by pile driver in river construction. Man struck by falling hammer at bridge site. Laborer crushed at pier foundation work. They didn't make front page headlines. They appeared in back pages, in brief notices, in lists of accidents alongside fires and runaway horses. They were expected. The cost of building a bridge. The bodies were removed. A prayer might be said. The work continued. The next pile was positioned. Then there were the chains. The chains that lifted the hammer were under enormous stress. Heavy iron links, each one forged and welded, cycling up and down thousands of times a day. Metal fatigues. Links stretched, welds failed, wear accumulated. When a chain broke under load, it whipped. Imagine a metal snake, each link weighing several pounds, suddenly released from enormous tension, lashing across the deck of a barge or the frame of the driver. Men lost hands, lost arms, lost eyes, lost their lives. The chain became a weapon, indiscriminate and lethal. And the hammer? When the chain broke, the hammer dropped, wherever it was in the cycle, onto whatever was below it. Sometimes that was an empty guide frame. Sometimes that was a man. The steam engine itself was a danger. Boiler explosions were common in the 19th century. Every few months, somewhere in America, a boiler ruptured. The pressure of superheated steam releasing all at once. Metal fragments flying like shrapnel. Scalding water and steam burning everything within reach. Men died in agony, their skin peeling away, their lungs scorched. Piledriver boilers were no exception. Work sites were remote. Skilled mechanics were scarce. Maintenance was deferred. Pressure gauges were unreliable when they existed at all. Engineers pushed their machines hard because the foreman was pushing them. And sometimes, the machines pushed back. A boiler explosion on a barge in the middle of a river meant no escape, nowhere to run. The steam killed everyone within reach. The force of the explosion could destroy the barge itself. Men were thrown into the river, scalded, injured, drowning in muddy water far from shore. Working on the water added another dimension of risk. Many pile drivers operated from barges, floating platforms that could be positioned wherever foundations were needed. These barges rocked. They shifted with current, with wind, with the impact of driving itself. Every blow of the hammer transferred force into the barge, making it shudder, making the deck unpredictable. Men worked on surfaces that moved constantly, surrounded by machinery that didn't care about their balance. A stumble near the edge of the barge meant falling into the river. The water at a pile driving site was not clean water. It was churned mud, debris, timber fragments, sawdust and bark. Visibility was zero. Falling in was disorienting. Which way was up? Which way was the barge? Climbing out was difficult, especially if you were wearing heavy boots, heavy clothes, carrying tools. And if you fell near the piles themselves, there were metal points below the surface. Iron shoes on driven piles waiting to impale you. Submerged timber waiting to trap your legs. Strong currents waiting to sweep you away. In winter, they kept working. The railroad didn't stop for seasons. Bridges needed to be ready when the line reached them, and lines were reaching new territory every month. So men drove piles in December, in January, in February, when ice formed on the river and the wind cut through every layer of clothing. Standing on frozen barges, operating steam engines that became temperamental in cold weather, handling metal that burned exposed skin on contact, watching your breath freeze before your face while sweat soaked your back from the labor. Frostbite was common. Hypothermia was common. Men who fell in during winter driving were sometimes dead before they could be pulled out. The cold took them in minutes, and their bodies were sent home on the same railroad they'd been building. If their bodies could be recovered at all. Some crossings took years. The bridge over the Missouri at Kansas City required piles driven to bedrock through 60 feet of unstable silt that wanted to swallow everything. The bridge at Poughkeepsie needed foundations in the Hudson's treacherous tidal currents. The bridge at Memphis faced floods, ice, and soil that seemed determined to reject every pile driven into it. These projects ate men. Not in a single disaster, not in one dramatic accident, in a slow accumulation of injuries and deaths over months and years. A man crushed here, a man drowned there, a boiler explosion that killed 3, a chain failure that maimed 2 more, a worker who simply disappeared, fell in and never came up, body never found. By the time the bridge was done, the casualty list might include dozens of names. Names that appear nowhere on the commemorative plaques. Names that no history book records. Names that even the companies involved tried to forget as quickly as possible. If you've made it this far, subscribe. This is the content I make. The stories behind the infrastructure everyone takes for granted. Now let me tell you about the scale of what these machines accomplished. Because the individual bridges were just pieces of something much larger. The railroad expansion of the 1850s through the 1890s was the largest construction project the world had ever seen. Nothing before it compared. Not the pyramids, not the Great Wall, not the Roman roads. Nothing since has matched it in proportion to the resources available at the time. Consider the numbers. In 1850, America had approximately 9,000 miles of railroad track. By 1900, that number exceeded 190,000 miles. In 50 years, the country laid more than 180,000 miles of new track. That's more than 7 times the circumference of the Earth. And track doesn't just cross flat ground. It crosses obstacles, rivers, ravines, swamps, valleys. Each obstacle required a bridge. Small streams needed timber trestles, simple structures that might require only a handful of piles. Larger rivers needed serious structures with multiple piers. Major crossings needed engineering marvels, bridges that became landmarks, bridges that took years to complete. Estimates suggest the railroad system required at least 70,000 bridges by 1900. Some historians put the number higher. Many of these were simple affairs, wooden trestles spanning dry washes in the desert. But thousands were major structures over significant water. Each one of those bridges started with piles. Think about the timber alone. If each bridge required an average of 100 piles, and each pile required a 40-foot log, we're talking about millions of logs. Between 5 and 10 million wooden piles driven during the railroad era. Some estimates suggest the number could be higher still. Entire forests cut and transported to construction sites. Logging operations that cleared hillsides from Maine to California. The Douglas fir forests of the Pacific Northwest fed the western railroads. The white oak stands of the Midwest fed the central lines. The cypress swamps of Louisiana fed the southern routes. Trees that had been growing for centuries were felled, shaped, and pounded into mud within a span of decades. The ecological impact was staggering. Not just the trees removed, but the ecosystems disrupted. Beaver dams destroyed, stream beds altered. The natural impediments that had slowed water flow for thousands of years removed and replaced with driven timber. Erosion patterns shifted. Sediment moved differently. Fish spawning grounds were destroyed or changed beyond recognition. I don't say this to condemn the men who did the work. They were building a nation. They were creating connections that would transform American life in ways nobody fully anticipated. But there's a cost to progress. There's always a cost. And part of that cost was borne by the land itself. The steam pile drivers worked in every conceivable condition. Desert crossings where water for the boilers was scarce and had to be hauled for miles. Where the sun blistered exposed skin and metal became too hot to touch by midday. Mountain crossings, where thin air reduced engine efficiency and freezing temperatures turned lubricants to sludge. Swamp crossings, where mosquitoes carried malaria and yellow fever, where the ground tried to swallow machinery whole, where men worked standing in water up to their waists. The Great Northern Railway pushed through Minnesota swamps, where piles had to be driven through 30 feet of peat before finding anything resembling solid ground. Peat that compressed and shifted, that wanted to squeeze the piles back out, that required constant monitoring and adjustment. The Southern Pacific crossed the Salton Sink, where summer temperatures exceeded 120 degrees, and men collapsed from heat exhaustion daily. Where water was so scarce that steam engines competed with workers for every drop. The Transcontinental Railroad, completed in 1869, required pile work at dozens of sites along its route. The Central Pacific built trestles across the Sierra Nevada valleys. The Union Pacific bridged countless prairie streams as it raced westward. When the Golden Spike was driven at Promontory Summit, it connected two lines that had consumed millions of wooden piles between them. But I want to focus on one aspect that often gets overlooked: the floating pile drivers. When you needed to build foundations in the middle of a major river, you couldn't position your pile driver on land. The work was out there, in the current, away from any shore. So you put the pile driver on a boat, specifically on a barge. A flat-bottomed vessel, sometimes purpose-built, sometimes converted from other uses. The pile driver was mounted on the deck, a 40-foot tower rising from a platform that moved with every wave. The barge was anchored in position, using heavy cables attached to dead men on shore or to massive anchors dropped in the riverbed. These floating operations were engineering achievements in themselves. You had a tall tower, top-heavy with machinery, sitting on a platform that moved with every wave, every gust of wind, every change in current. The steam engine had to function on a surface that wasn't quite level and kept changing its angle. The crew had to work around equipment that shifted underfoot. Positioning was critical. The barge had to be placed exactly where the pile needed to go. Not approximately, exactly. Within inches. This required constant adjustment, pulling on one anchor line while releasing another, fighting the current that never stopped trying to push you downstream, fighting the wind that came and went unpredictably, sometimes spending hours just getting into position before a single blow could be struck. In rivers with strong currents, this was exhausting, dangerous work. The Missouri, the Ohio, the Mississippi, these were working rivers. Cargo vessels passed constantly. Steamboats, flatboats, rafts. Each passing vessel created waves that rocked the barge. Each change in water level, from rain upstream, from seasonal variation, required adjustment. Ice jams in winter could sweep through and destroy an entire operation in minutes. A barge that had taken weeks to position, equipped with expensive machinery, crewed by experienced men, could be crushed against a bridge pier or swept downstream by ice that moved with unstoppable force. The bridge over the Mississippi at Rock Island, completed in 1856, was the first railroad bridge to cross the Father of Waters. Its construction required floating pile drivers to work in a river a half-mile wide with treacherous currents and constantly shifting sandbars. The men who drove those piles worked in conditions that most modern workers would refuse. Rocking platforms, freezing water, machinery that could kill them at any moment, for wages that wouldn't pay a modern worker's phone bill. Less than 2 weeks after it opened, a steamboat struck the bridge and caught fire. The resulting lawsuit went all the way to the Supreme Court. Abraham Lincoln, not yet president, argued the case for the railroad. The river interests, the steamboat operators, argued that the bridge was a hazard to navigation, that it should be torn down. The bridge won. But the real victory belonged to the men who had driven its foundations into the Mississippi's mud. Hundreds of piles, each one hammered into place from rocking barges, while the river tried constantly to sweep them away. The Eads Bridge at St. Louis, completed in 1874, pushed engineering further. James Eads refused to use wooden piles for his main supports. He wanted to reach bedrock, more than 100 feet below the river surface. He used pneumatic caissons, pressurized chambers sunk into the riverbed while workers dug inside them. Men worked in compressed air, suffering from caisson disease, dying from conditions that wouldn't be understood for decades. But even Eads needed pile drivers, for the approach spans, for the cofferdams that let him work in the river, for the temporary structures that supported construction. The steam pile driver was there, doing its work, even on the most advanced bridge project of its era. And those approach spans? Still standing, still carrying traffic, over 150 years of river floods, earthquakes, temperature swings, and constant use. Built on wooden piles driven by steam power before electric light was common. That brings me to something most people don't realize: the longevity of this work. Wooden piles, driven below the water table, can last essentially forever. I'm not exaggerating. The conditions that destroy wood, rot, and insects require oxygen. Submerged piles exist in an oxygen-poor environment. The bacteria and fungi that break down wood can't survive there. The insects that eat wood can't reach there. It's the same environment that preserved Viking ships, Roman wrecks, ancient forests in peat bogs. Wood that would rot in a decade above ground lasts centuries underwater. In Venice, archaeologists have studied piles driven 1,000 years ago. The wood is still sound, still strong, still doing its job. The grain is intact. The structure is solid. They could drive a train over those piles today if someone built the track. American bridge foundations from the 1850s are still in service today. Not all of them. Many have been replaced as loads increased or structures were upgraded. But some remain. Wooden piles driven by steam, still holding up bridges that carry modern traffic. The New York Central's crossing of the Harlem River used foundations driven in the 1860s. Multiple railroad lines in New England rest on piles that predate the Civil War. When engineers core sample these ancient supports, they often find wood in remarkably good condition. The outer layer may show some deterioration. The interior is solid, good for another century if left undisturbed. This is the legacy nobody sees. Underground, underwater, invisible to everyone who crosses above. An inheritance from men who have been dead for over 100 years. Their work is still working. But here's the philosophical weight of that legacy. Those men didn't know their piles would last this long. They were building for their time, solving their problems, meeting their deadlines. They were paid by the pile, by the day, by the bridge. When the job was done, they moved on. Next crossing, next project, next paycheck. They left behind something more permanent than they intended, more permanent than they imagined. They drove logs into mud, expecting decades of service. And some of those logs have served for a century and a half. Will serve for centuries more. That's worth sitting with for a moment. The workers who died on these projects, crushed by hammers or drowned in rivers or killed by boiler explosions, they died for something that lasted. Their sacrifice wasn't wasted. The bridges they built carried generations of travelers. The foundations they drove held up commerce, connection, communication. Every train that crossed, every carload of goods, every passenger reaching their destination, moved on something those men created. It doesn't undo the tragedy. It doesn't make the deaths acceptable. But it gives them meaning. A meaning the workers themselves may not have fully grasped. They were building the skeleton of a nation, piece by piece, pile by pile. Subscribe if this resonates. I make these videos because these stories deserve to be told. Now let me tell you about the transition, because the steam pile driver didn't last forever. Nothing does. And understanding why it faded helps you appreciate what it accomplished. The peak years were roughly 1870 to 1900. During this period, the steam pile driver was everywhere. Every major construction project, railroad or otherwise, employed these machines. Harbor improvements, dock construction, building foundations in waterlogged urban areas, seawalls, bridges of all kinds. The industry refined the technology steadily. Hammers got heavier. More efficient engines allowed faster cycling. Better metallurgy produced more reliable chains. The basic design remained the same: drop a heavy weight on a pile. But every component improved incrementally. Some manufacturers became specialists: Vulcan Iron Works, McKiernan Terry, Raymond Concrete Pile Company. They competed on power, on speed, on durability. Their catalogs from the 1890s read like technical poetry. Specifications for every condition. Hammer weights from 1,000 to 6,000 pounds. Leads adjustable for any angle. Optional features for difficult soils. But by 1900, the landscape was changing. Concrete was becoming practical for large-scale construction. Portland cement, mass-produced at reasonable cost, allowed engineers to pour foundations instead of driving them. Concrete could be formed into any shape. It could reinforce itself with iron rods. It could be placed in conditions where wooden piles were difficult to position. For certain applications, concrete piles emerged. Cast in forms on shore, cured until solid, then driven like wooden piles, but with greater bearing capacity. Or cast in place, poured into holes drilled into the earth, forming columns of artificial stone. Steel piles followed, H-beams driven point down. Sheet piles interlocked to form continuous walls. Steel could go deeper than wood, could carry more weight per pile, could resist conditions that would shatter timber. The steam pile driver adapted. The same basic machine that drove wooden piles could drive concrete and steel. The principle was unchanged: drop a weight, transfer energy downward. But the wooden pile, the tree trunk that had been foundation technology for millennia, began its retreat. It didn't vanish entirely. For temporary structures, for certain soil conditions, for projects where economy trumped longevity, wooden piles remained practical. They're still driven today, actually. Not with steam, with diesel hammers. With hydraulic systems. With vibratory drivers that shake the pile into the ground rather than pounding it. But wooden piles, the same basic concept the Romans used, still have applications in modern construction. And the bridges built during the steam era? They faced a different challenge. Not obsolescence of method, but obsolescence of capacity. The locomotives of 1870 weighed perhaps 20 tons. The locomotives of 1920 weighed 10 times that. Modern freight locomotives push 200 tons. The wooden trestle that carried the 1870 engine safely would collapse under modern rolling stock. Bridge after bridge had to be upgraded, replaced, rebuilt to handle loads the original designers never imagined. But here's what's remarkable. Often, when engineers upgraded these bridges, they found they could keep the foundations. The piles were overbuilt, driven deeper than strictly necessary, more of them than the original loads required. Whether by accident or intuition, the original crews had created foundations capable of more than was asked of them. So the superstructures were replaced. Wood gave way to iron. Iron gave way to steel. But underneath, the same wooden piles remained, taking the increased loads, shifting slightly to accommodate them, continuing to do their job. Today, if you drive across an old railroad bridge in rural America, there's a reasonable chance you're rolling over wooden piles driven by steam power more than 100 years ago. No marker commemorates this. No plaque acknowledges the men who placed them. They're invisible, underground, taken entirely for granted. But they're there, still working, still holding. Let me close with some numbers, because numbers give scale to what might otherwise seem abstract. 100,000 miles of railroad required an estimated 70,000 bridges. Those bridges required somewhere between 5 million and 10 million wooden piles, depending on whose estimates you trust. Each pile was driven by a steam-powered hammer, striking 40 to 80 times per minute for 30 minutes to 2 hours. Do that math. Millions of piles. Hundreds of millions of hammer blows. An entire generation of men whose primary job was standing next to a 2,000-pound weight as it fell, again and again, into soil that didn't want to accept it. How many men died? There's no Kim Day record. industrial safety tracking barely existed. Companies didn't publish casualty statistics. Workers' deaths were noted in company ledgers next to equipment costs and supply orders. Just another expense of doing business. But extrapolating from the fragmentary records that survive from newspaper accounts and coroner's reports and company correspondence, historians estimate that pile driving during the Railcade era killed at least one worker per 1,000 piles driven. Some estimates are higher, some much higher. GT death per 1,000 piles, and 5 to 10 million piles. The railroad foundations alone may have cost 5 to 10,000 lives. More than the entire Union death toll at Gettysburg, spread over 50 years, scattered across a continent, almost entirely forgotten. These men have no monument. Their names appear in no history books. Their contribution is buried, literally buried, under the infrastructure that made modern America possible. Every bridge you cross rests on something. The soil, eventually. But between the bridge and the soil, there are foundations. And those foundations, in thousands of cases across this country, are wooden piles. Tree trunks driven into the earth by steam-powered hammers, operated by men who risked their lives for wages that would horrify us today. They stood at the base of 40-foot towers. They listened, detriking wood. They breathed coal smoke and mud vapor. They positioned logs in guide frames while 2-ton hammers hung overhead. They did this work in summer heat and winter cold, on solid ground and rocking barges, in clear weather and pouring rain. And when the job was done, they moved on. Next crossing, next foundation, next bridge. No celebration, no recognition, just another job site, another steam whistle, another hammer beginning its rhythm. They didn't build monuments. They built what was underneath monuments. They built the invisible structure that everything else depends on, one pile at a time, 40 feet down, into mud, into gravel, into whatever the earth offered. They built the skeleton of America, and they built it to last. That's the story of the steam pile driver. The machine that made railroad bridges possible. The machine that demanded blood as payment for progress. The machine that most people have never heard of. Doing work that most people never think about. Building foundations that most people never see. But they're there, under every old bridge, under every causeway, under the tracks that still carry freight across this country. The piles are there, driven by steam, driven by men, still holding, after all these years, still holding. Thank you for watching.